Consider this wire. Current I is in the upwards direction as shown. We can imagine this wire made up of small elements. Every element creates magnetic field around it. That is why we experience magnetic field around the wire. Let us focus on one element of this wire. This element is of small length, dl. The letter D shows that its length is very small. You can think of this length like a 2-3 cm piece of a wire. Remember, there was current I flowing upwards through the wire. As this element is the part of the wire, same current I will flow through it. We can say now current I is going through length dl. We call this I dl the current element. Current element is a vector quantity. It means it has both magnitude and direction. Its direction will be same as the direction of current. And magnitude is just multiplication of I and dl. The current element creates magnetic field in closed loops around it. Magnetic field direction will depend on how the current element is placed. At this position the current element has upward direction. Now the direction is downwards, the magnetic field directions will also change. In this position the magnetic field lines are in counterclockwise direction if we see from the top. Now the direction of magnetic field is clockwise as seen from the top. We can easily know this by using right hand grip rule. If you grip the wire from your right hand and point your thumb in the direction of the current, like this, your fingers will curl in the direction of the magnetic field, that is clockwise direction. This is the direction of magnetic field. Try by yourself. Grip the wire from your right hand and point your thumb in the downward direction. Your fingers will curl in clockwise direction. To show these magnetic fields in our notebook, we can either try to draw ellipses shown here with arrow tip to show direction of magnetic field. Or you can use vector notations in your notebook. We use cross sign to show magnetic field line vector going inside the page. And dot sign to show magnetic field line vector coming out of the page. So if you have these signs around the current elements, we can say that the magnetic field lines are going into the page at the right side, which we are showing by cross sign, and at the left side they are coming out of the page, which we are showing with the dot. Let us take one point P around this element and calculate magnetic field magnitude at this point. What all we need to know? First, we need current element or IDL. Second, we need the distance between current element and point P. We will call it R. Third, we should know the angle between IDL vector and R vector. We can call this angle theta. According to Biot Savart law, the magnetic field at point P will be directly proportional to the current element. It means if current or length, or both are increased, we will get more magnetic field. Also magnetic field will be directly proportional to the sine theta. It means we will get maximum magnetic field at 90 degrees to the current element, as sine theta gives maximum value of 1 at 90 degrees. But magnetic field will be indirectly proportional to the distance r squared. So as we go away from wire, the magnetic field will decrease. To remove the proportionality sign, we need to use a constant, mu naught by 4 pi, where mu naught is called permeability of free space. We can calculate the magnitude of the magnetic field using this formula. For direction, we can use right hand grip rule. The magnetic field at point P will be going into the screen, so we can show it by cross sign.